All right, and welcome back. This is Wednesday's lecture, part 1. So we're going to be continuing on with chapter 20. So now we're on 20.3. So we've talked about electric forces and we've talked about magnetic forces, but we haven't talked about what happens when we have them played together. So now this is the part of the book where we really start, I just love it. We're going to really start bringing together all of these different concepts that we've been learning all year and do what I think is some very cool physics. All right, so it would make sense that if we have a particle with charge that is moving in both an electric field and a magnetic field, it will experience a force from both. So remember, we have a moving particle and a magnetic field. So you've got a magnetic force and you've got a moving particle. You have a charged particle, so it always experiences a force from any electric field. So you're going to get the magnetic force, Q, V cross B, corresponding to the particle's velocity and crossed with the magnetic field, and you're going to get the electric force, which is equal to Q times the electric field vector. So we can combine these together, so we would sum the total forces. So total force is equal to Q times E plus Q V cross B. And this is known as the Lorentz force. All right, so this is a very powerful equation. And we will be slowly building more and more applications about it. But let's talk about what happens so that you could arrange these forces in a way that they essentially equal 0. So how do you arrange the forces to equal 0? And essentially what we mean by equal 0 is they're not going to impact the particle's velocity. It's going to go in a straight line. So one possible arrangement, so we have our y, x, and z axis. You could arrange your field such that you have your electric field here, and you've got your velocity in this direction, and then you have your B field. So one possible arrangement, and on your own, think of a few more. So this is one possible arrangement. Now notice, all three factors, the electric field, the magnetic field, and the velocity, needed to be arranged in a particular way. And so essentially, for the 0 situation, the magnetic field and the magnetic and electric forces must be equal and opposite. So EE would be equal to EV B sine of 90. And so, of course, we would see E is on both sides. So the electric field is equal to the velocity times the magnetic field. So any arrangement of the electric and magnetic fields with directional velocity that gives you this result is going to be a situation where a particle is going to go in a straight line. All right. So building on this concept, let's think about if you were to make some changes. So we're going to say we've started out with E being equal to VB, so we've got equal and opposite, so that there's the net force is equal to 0, so such that F net is equal to 0. Now let's say we have a particle that comes in, same Q, so same charge for this setup, but a slower velocity. So what happens? Well, then the electric field is no longer equal to VB. So E has stayed the same, B has stayed the same, V is now smaller. So in this case, the particle will not move in a straight line. So the particle will experience a net force of non-zero and interaction occurs. So a deflected path. Okay, so what about, and I can write this out more explicitly, so QE greater than QVB, F net not 0. So what about a particle with the same V as our original setup, but a minus Q. So, and this would be the magnitude of minus Q is equal to the magnitude of our positive Q. So this still, we've got a situation where we're going to get a straight line path. So if you think about it, if we set this up, QE may be equal to QVB, and you do this to both sides, you still have a situation where they're equal to each other. The main components have all stayed the same. So F net still 0. And the electric and magnetic forces are flipped. All right, so what are the main takeaways of this discussion? Regions with perpendicular fields, so that would be E and B, will allow particles of particular velocities and so that would include both the speed and direction to pass through no deflection. Which is pretty useful if you're doing particle physics research or manipulation. So basically, E cross B points in the direction of the allowed velocity. And then you could scale it using EVB. So you get the direction from E cross B, and then you could solve for velocity to get the speed that is allowed. So this is the direction that's allowed, this is the speed that is allowed. Pretty cool stuff, I think. Okay, so let's do an example. So we have a 5-turn circular loop of wire with a radius of 60 centimeters with current I. See, you thought you'd be done with the drilling, but oh no, no, no. I make sure to bring it with me. Okay, so there is a charge of Q is equal to positive 1.2 coulombs at 120 centimeters, or 2 times the radii to the right. Of the center. I'll draw a picture of this setup too. I'm just writing the complete problem out since I know it's a little bit different than lecturing at the board. All right, so an alpha, so that would have charge 2e, positive, traveling upward with a speed of v is equal to 4.6 times 10 to the 4 meters per second, passes through the center. So in this moment, by definition of the problem setup, F net is equal to 0. And we're going to make some assumptions. B Earth is negligible. All right, so what is the magnitude and direction of the current I? Okay, and our starting point is that the magnetic force plus the electric force is equal to 0. And of course, we get this from looking at this statement here. Okay, so the way to approach this problem is you want to start out symbolically and think through what's going on to get direction, and then we can actually plug in some numbers. Okay, so I'm going to go ahead and draw a picture of our setup. So we've got our wire, we've got 5 turns, 2, 3, 4, 5, which are of course perfect circles. We can play pretend in this class. So 5 turns. The radius R is equal to 60 centimeters. And we have our plus Q over here of 1.2 coulombs. And this is located 2R from the center of the circle. And we have our our alpha particle. It's an alpha going up, and it has velocity in the moment of interest of 4.6 times 10 to the 4 meters per second. So those of you that are better artists, by all means, feel free to improve upon this drawing. All right, so the electric field from this positive particle, so remember, positive radiates outward, just like positive people. So if it's going to radiate outward, it's going to be in negative x. So from our positive Q. So the electric force on our alpha, which recall is positive, is also in negative x. So positive particles go along with their electric fields, negative particles go against the electric field. So it's just like positive and negative personalities. So we've been working with that idea in our head. I'll stick with it. If the mnemonic device is working, why mess with it? By the way, I miss all of you and the positivity that you bring into my classroom. It would be way more fun to interact with you right now. All right, so we've got our alpha particle. We know what direction the electric force is in, and so we also know, try to bring in some more colors here, that our magnetic force must be equal and opposite based on the setup. So it's going in the opposite direction here. Okay, so let's keep going along with this. So as Q is a positive particle, so it's an alpha, it follows that V cross B is in the same direction as F magnetic. So building on this, we have our velocity going up, we have our magnetic force, and then we know then that V cross B must be in that direction as well. All right, so we're going to have to use the right-hand rule and a little bit of trial and error. So remember, the product of the cross product using the right-hand rule is going to be the direction your thumb is pointing in. So if we point our thumb in that direction, we see that our fingers have to be pointing up. So therefore, the magnetic field B must be out of the page. Okay, so we used right-hand rule to get B. Now we can use our current, and by that I would mean current like a flow of charges, not current situation, right-hand rule to get direction of I. So if B is pointing out, our fingers curl this way, which is counterclockwise. So I is counterclockwise. There you go. And I really encourage you to practice this and practice this and practice this, especially if it doesn't come naturally to you. And I'm saying this as someone for whom the right-hand rule does not come naturally to. Okay, so we know the direction of current, so I is counterclockwise. So part of our answer is done. Now we can go after the magnitude of current. It's counterclockwise. Okay, so now we're going to bring our equations out to play. So F net, we know, is equal to 0. So the magnitude of the magnetic force must be equal to the magnitude of the electric force. So reasonable starting point, F net to be 0. There's nothing else in the surroundings. It's bringing a force. So these are the only two things that we are contending with. So the magnetic force And actually, in my work, I have put the electric force on the left-hand side, so I'm going to go ahead and move this around right now, so it's just more consistent with the work that I've done. So our electric force, 1 over 4 pi epsilon naught, so our charge is going to be 2e for the alpha particle, times q for that 1.2 coulomb positive charge, over 2 times r, so that would be the distance, squared is equal to the magnetic force, which is going to be 2e for the charge, times the velocity, times the magnetic field. So let me bring in, this is the setup that I have just used for these equations. So same picture as before. We can see our positive charge here. Here's the alpha, and we can see that this is 2 radii from the center, and that, of course, the radius is 60 centimeters or 0.6 meters. Okay, so moving right along, we want to go ahead and find our magnetic field. So let's bring that over to one side. B is equal to 1 over 4 pi epsilon naught 2eq over 2r squared. And this is definitely one of those situations where you really want to just leave everything symbolic until the end. Okay, so we can see we have a 2e here and a 2e there, so that just makes a nice little 1. And so B is equal to 1 over 4 pi epsilon naught q over 2r quantity squared times 1 over v. And we'll just rewrite that, 1 over 4 pi epsilon naught. Since that's a constant, we're going to leave it all together for now. So q over 4v r squared. So all I've done is just bring the v in, and I went ahead and squared out that 2 to have a 4. All right, so let's go ahead and remember that this is important. Now, at the beginning of the problem setup, I said that we are dealing with a loop. And if you recall, the magnetic field of a loop is equal to mu naught over 4 pi, 2 pi r squared over I, divided by z squared plus r squared to the power of 3/2. This is for the generic loop. Again, chapter 17. Yeah, chapter 17? 17. And at the center, B is equal to mu naught over 4 pi, 2 pi I over R. All right, so this is useful. So we know that we're at the center of the loop. We have derived B given the condition that the magnetic and the electric field must be the same. And we know because we are at the center of the loop, these two must also be equal to each other. And this is very useful because ultimately we are after current, which is in the expression for the magnetic field at the center of a current carrying loop. So we can set these two equal to each other and we can go after I. And also, one more thing to note about this, so there are 5 loops. So we need to have 5 times B loop. Okay. So B is equal to 5 times mu naught over 4 pi, 2 pi I over R. And now let's go ahead and set this equal to our other expression for B. So we have 1 over 4 pi epsilon naught Q over 4V capital R squared is equal to 5 mu naught over 4 pi, 2 pi I over R. So if we bring I over to one side by itself, because that's what we want, I is equal to R over 2 pi times 4 pi 5 mu naught times 1 over 4 pi epsilon naught Q over 4 VR squared. So let's go ahead and do a couple of cancellations. So this is going to cancel that squared. We have a 4 pi here and a 4 pi there. Okay. So I is equal to 1 over mu naught epsilon naught Q over 40 times pi RV. So 2 times 5 is 10, times 4 is 40. All right, so at this point, we now have an expression for current in terms of all things we know. Mu naught and epsilon naught are both constants that we're familiar with. Q was given at the beginning of the problem. Pi, everybody better know what pi is. By the way, happy belated Pi Day. The radius was given, and we've got the velocity. Okay. Let's double check one thing. We're good. Okay, so we have 1 over 4 pi, not an x, times 10 to the minus 7. That would be the constant for epsilon naught, times 8.85 times 10 to the minus 12, the value for, sorry, this is mu naught, this is epsilon naught, times 1.2 coulombs given, times 40, times pi, times 0.6 meters for the radius, times 4.6 times 10 to the 4 meters per second, and we get a current of 3.1 times 10 to the 10 amps or coulombs per second. And this is going counterclockwise. All right, so there you go. So this ends part 1 of Tuesday's lecture.